My name is KaiLian, and this summer I worked on a project called the role of adhesion torque on spiky particles deposition. So what are colloidal particles? Colloidal particles are small particles suspended in a different medium, such as a solid, a liquid, or a gas. Individual particles pack together, and this collective behavior is what makes them so advantageous. The stability of a colloidal dispersion is based on these packing patterns. Here's an example of a spherical particle's packing patterns. And these packing patterns are affected by a particle's shape and geometry, so differently shaped particles will pack together differently and thus have different stability in a dispersion. Researchers have come up with a variety of novel synthesis methods that have resulted in many different kinds of particles being produced. And since when you change a parameter of the particle, the physiochemical properties can be changed, this allows for an even wider range of possibilities. These particles can be classified according to differing size, surface chemistry, composition, and shape. Here are some examples of the different ways that these particles have been classified. Colloidal particles are of interest because since they can be engineered to fit a wide variety of sizes and shapes, they can be applied to many different fields and industries. Their uses are extremely versatile, and research is currently going on at the theoretical, experimental, and even in the clinical level. So for my project, I decided to focus on a specific kind of particle known as the spiky particle. The spiky particle is an anisotropic particle, which means that when the directionality or the orientation of the particle changes, its physiochemical properties change. And the reason why I find spiky particles so interesting is because of the prevalence of their shape in nature. For example, pollen, which is shown here, is an example of a spiky type of particle. And in nature, there are spiky particles of all different kinds of scales that range from nanometers all the way to micrometers. Besides the spiky particles found in nature, researchers also study a different kind of spiky particle, shown here, known as a synthetic bio-inspired spiky particle that has branchy types, including the octopod, the hexapod, and the tetrapod. So I decided to study the spiky particle because I find it interesting that even though there are so-called facts against nature about the spiky particle, that it is still extremely prevalent in nature. For example, a spiky particle's spikes of different length contribute to its roughness. And we know that roughness is bad and decreases the interactions between a particle and the surface. We also know that because of the spikes on a particle, there is a decreased surface area of which the spiky particle would come into contact with a planar surface. And we know that decreased surface area is bad and decreases interactions as well. So that led me to ask, what is the scale of the roughness with respect to the particle size? And how does this influence the particle's adhesion? In my project, I looked at the interaction between an individual spiky particle and the planar surface. I constructed my spiky particle using a spherical core and superellipsoidal or ellipsoidal spikes of different lengths. I calculated the interaction energy between the particle and the surface as a function of orientation and separation distance. I changed the orientation by changing the Euler angles of the spiky particle, which are theta here, psi, and phi. I mainly focused on phi and psi because when the angle of theta changes, it doesn't change the point of contact between the spiky particle and the surface, because it would just be rotating around like this. However, when phi and psi change, which would be rotating around like this or like this, it does change the point of contact. I also looked at the separation distance, represented here by h, which shows you how far away it is from the planar surface and would change based on the roughness of the particle. I based my spiky particle off of a common sunflower pollen particle. I did this by reconstructing a spiky particle over an image that I had found. I started with a spherical core, and then using the phi, psi, and theta angles, I directed the spikes outward in order to match the initial orientation of these spikes. I came up with a mesh rendering of the original particle, and I used this along with the surface element integration technique in order to find the interaction energy. Now, while the spiky particle's core remained spherical, I wanted to change the parameters of the spikes. I decided to change the spike's shape and the spike's length. On the left here, you can see that when R and N are equal to 1.3, it produces a supersphere shape. And another supersphere shape is produced when R and N are equal to 1.6. When R and N are equal to 2, it produces a spherical shape. By lengthening these supersphere shapes, you can get superellipsoids and ellipsoidal shapes. So, to change the aspect ratio, I increased the Z aspect ratio of the spike with respect to the X aspect ratio in order to lengthen the spikes, giving me superellipsoidal shapes and ellipsoidal shapes, as well as longer spikes. Overall, my project modeled 3 different things in order to show the role of adhesion torque on the interactions between the spiky particle and the planar surface. I modeled a gold spiky particle at the micron scale, and I chose gold because it's biocompatible, and I chose the micron scale because it's the same scale as the pollen I reconstructed my spiky particle after. I also wanted to find the DLVO energy as a function of separation distance and orientation. This energy is based on the van der Waals energy and the electrostatic energy. And the DLVO theory postulates that the overall potential energy of the interaction can be found by this function of separation distance and orientation. I did this by plotting the particle's overall orientation using the polar angle and the rotor angle. I also wanted to model the adhesion based on the roughness of the particle, and I did this by varying the spike length and shape to increase the roughness. This resulting DLVO energy landscape was analyzed with a directional torque in order to show this effect of changing surface area, Gaussian curvature, and roughness. Here are my initial results of the interactions between the spiky particle and the planar surface before the directional torque was applied. As you can see, this particle has a radius of 1 micron. The aspect ratio of the spike's lengths are 15. The core size is 10.4, and the shape of the spikes is n equals 2, which is ellipsoidal. This graph here on the left is the separation distance. This distance measures from the center of the particle all the way to where the particle touches the surface. The spots here where I'm marking in blue, the darkest red, are where the spike is perpendicular to the surface. This is the maximum distance between the particle's center and all the way down the length of the spike. Conversely, these spots here in the middle that have the more minimum separation distance are when multiple spikes are contacting the surface at one time, because as the spike rotates, that distance is going to decrease. This graph correlates with the DLVO energy landscape here on the right, which measures the potential energy of these interactions in kT, and also is plotted as a function of phi and psi. So here where I circled these dark red spots, we also have these same spots. And where I'm circling here is also where only one spike is touching the surface perpendicular. But these spots here in the middle are where the particle is having multiple spikes touch, just like in the separation distance graph. So these graphs kind of help you to understand the orientation of the spiky particle at the surface. And the equilibrium energy landscape, so the ideal position for that spiky particle to be in, is the more negative it gets. So this dark blue would represent the equilibrium energy for that particular energy landscape. The first parameter I looked at was the influence of the spike length. I kept the spike shape constant at n equals 2, which is ellipsoidal, and the core size constant at 10.4. To increase the length of the spikes, I changed the aspect ratio of the spike length from 12 to 15 to 25. As the spikes get longer, the roughness of the particle also increases, so the roughest particle is the one with the aspect ratio of 25 on the very right. Here are the DLVO energy landscapes with the directional torque fields applied. Something interesting to note is that even though the roughness of the particle changes with the spike length, the energy profile shapes basically stay the same. What I mean is that these scales here are basically the same shape in each of these DLVO energy landscapes. The roughest particle, the one on the right, also has a slightly different torque field than the others. This is because the energy in this landscape makes the torque field direct into the surface and below the surface, rather than above the surface like the other two. As I spoke about before, attractive energy occurs at energy minimums. Something interesting about the roughness of the particle is that as the particle gets rougher and the spikes get longer, the energy becomes less attractive. The aspect ratio of 25 doesn't even have any negative attractive energy as compared to the aspect ratio of 12. I'd also like to speak about the parts on this graph that represent where the one spike hits and where the multiple spikes hit. As I talked about before, the spaces in the middle of the graph here are where one spike is contacting the surface in a perpendicular fashion, whereas the spikes in the middle of these scales are basically where there is multiple spikes contacting the surface at once. Torque is greatest in regions with large energy variations, which happen to occur between these areas, which is basically where there are multiple spikes contacting the surface at once. So, from this we can gather that the multiple spike surface interactions promote torque. What I mean by that is that when there are more spikes hitting the surface at once, there is a more stable equilibrium energy that occurs. This can kind of be compared to an anti-rolling effect. When only one spike is touching the surface, it is a bit unstable, but as more spikes touch the surface, it is more stabilized. The other parameter I looked at was the influence of the spike shape. I kept the spike size constant at a length of 10, and I kept the core size at 7.6. I changed the spike shape from the superellipsoidal 1.3 and 1.6 to the ellipsoidal shape of n equals 2. The superellipsoidal shapes both have more Gaussian curvature than the superellipsoidal shape of n equals 2. Again, here are the dLVO energy landscapes with the directional and torque fields applied over them. I would also like to point out that even though the spike shape changed, again, the shape of this energy profile did not change across the graph. So, the ideal equilibrium orientation, again, is this space where multiple points of the spikes are contacting the surface at one time. Whereas, again, when only one spike is contacting the surface, that there isn't much torque that exists there. The torque is greater in the regions with a larger energy variation, and in this case, this happens to be in the graph of the spike shape of n equals 2, which is the one with the least Gaussian curvature. Overall, we successfully developed a methodology to study the particle surface interactions of spiky particles. These initial results explain the prevalence of spiky particles in nature despite the so-called facts against nature I spoke about earlier, including the decreased surface area of interaction and the roughness of the spiky particle. As many spikes contact the surface, there is a resistive torque generated which prevented the particle rotation. We saw in the torque directional fields that the energy equilibrium position occurred when multiple spikes contacted the surface at once. So instead of one spike only contacting the surface, when more spikes contacted the surface, it promoted an anti-rolling effect promoted by the torque at that position. And whereas spike length and spike shape did not affect the energy surface profile, particles with less roughness were shown to have more attraction. So basically, even though the spike shape and the spike length changed, the shape of the energy profile of each of the graphs was basically the same, only the potential energy of the graph changed. However, when the spikes were lengthened and the particle was more rough, there was less attraction. The roughness also created an energy barrier that stabilized the particle at different orientations over the surface. So there was also a torque effect with the roughness as well as in the Gaussian curvature, which, as the Gaussian curvature increased, the adhesion energy decreased. In the future, I hope to extend this work to different geometries, particle shapes, and other types of surfaces. Thanks for watching! Now I would like to thank the Honors College, Dr. William Wilkerson, and David Cook for allowing this project to be possible. I would also like to thank my mentor, Dr. Torres-Díaz, for his guidance and help in my project. If you have any questions, please feel free to contact me.